These gigantic black holes lurk at the center of galaxies. We have one right in the center of the Milky Way galaxy.
First of all, the black disk in the center is the event horizon.
Black holes have long been one of the most mysterious and fascinating phenomena in space. They're like cosmic vacuums, sucking in everything around them, even light. It's been an age-old puzzle for scientists. But now, renowned physicist Michio Kaku believes we finally found what's inside a black hole. Recent scientific revelations have taken us by surprise, promising insights that will unravel the profound mysteries within these cosmic giants. So, is there a gateway to alternate realities concealed within the dark confines of a black hole? Join us as we delve into the groundbreaking discoveries that might just reveal what's really inside a black hole. Cosmic magnets of unimaginable power and importance. Black holes are cosmic mysteries that continue to intrigue and baffle us. Their mysterious nature is like a magnet, drawing in our curiosity and challenging our understanding. Within this enigmatic realm, time behaves in ways that defy our expectations, confounding even the brightest minds. This leads us to ponder, what truly defines a black hole, and why does this seemingly space hold such immense importance and power? At the heart of it all is gravity, the force that tugs at everything. For black holes, it's as if gravity has been dialed up to its maximum intensity. But let's delve deeper into this cosmic spectacle. Black holes emerge from the remnants of deceased stars, specifically the remnants known as stellar cores, colliding in a colossal clash. When these remnants accumulate to about 3 times the mass of our Sun, gravity asserts its dominance, overpowering all other forces. This ultra-potent gravitational force compresses everything intensely, birthing a black hole. These peculiar cosmic entities stand out for their incredible density, exerting a gravitational pull so strong that even light succumbs to its grasp. Astronomers widely concur that most spiral and elliptical galaxies host black holes at their central cores. To categorize and understand these cosmic phenomena, we classify black holes into 3 primary groups. First in line are the stellar mass black holes, the smallest among them, typically ranging from 1 to 100 times the mass of our Sun. These black holes originate from the collapse of massive stars due to gravity, often culminating in dramatic events like supernova or stellar explosions. On the flip side, we have the heavyweight champions known as supermassive black holes. These colossal entities tip the scales into the millions or even billions of times the mass of our Sun. Scientists believe they reach such astronomical sizes by merging with other black holes and gobbling up nearby stars. Now, somewhere in the middle, we find the intermediate mass black holes. Although not as common, with only a few confirmed sightings, these black holes are estimated to weigh in between 100 and 100,000 times the Sun's mass. Michio Kaku suggests that these intermediate mass black holes play a key role in the formation of supermassive black holes through a process of mergers and accretion. Beyond just helping us understand how certain stars move and contributing to our knowledge of galactic structures, black holes open up a whole new frontier in physics for the scientific community. They're like uncharted territory, inviting researchers to explore and unravel the mysteries that lie within the vast reaches of the cosmos. Earth, Moon, and black holes. Albert Einstein's revolutionary concepts in his theory of general relativity have opened the door to an incredibly captivating concept: how entities in the universe influence the fabric of space and time itself. This influence is what we understand as gravity, the force that prevents everything from drifting away into the vast expanse of the cosmos. Let's delve into the realm of black holes. These cosmic enigmas are like the ultimate mysteries of space. They comprise an immense amount of material squeezed into an incredibly tiny space, and as a result, they possess an astonishing gravitational pull, akin to a compelling space magnet. Scientists are captivated by them because their extraordinary strength challenges and reshapes our understanding of the universe's fundamental principles. The truly mind-bending aspect is attempting to fathom what resides at the heart of a black hole, a point referred to as a singularity. The forces in play here are staggeringly immense. leaving scientists grappling with the complexities and mysteries that defy conventional understanding. Einstein's theory suggests that when something is drawn into a black hole, it seemingly vanishes completely, gone without a trace. However, another substantial theory, quantum mechanics, contradicts this notion. It presents a conflicting idea that such an occurrence cannot transpire. Consequently, black holes become a battleground where these two significant theories collide, challenging scientists to reconcile and integrate these disparate frameworks. While many envision black holes as literal holes in space, that portrayal isn't entirely accurate. Instead, consider them as super-intense cosmic magnets, exerting gravitational forces far more potent than anything we've encountered on Earth. Earth's gravity keeps us rooted, preventing us from floating away when we leap. But black holes? Their gravitational pull surpasses Earth's by an immense magnitude, drawing in objects with an intensity unparalleled elsewhere in the universe. What distinguishes black holes is their strange absence of any discernible surface to halt an inexorable descent, creating the impression of plunging into an infinite abyss, hence the moniker black holes. These enigmatic cosmic whirlpools commence their existence through the dramatic collapse of a massive star, compressing an astronomical amount of material into an incredibly compact space. Picture condensing an entire star into a minuscule dot. When an immense quantity of material is packed into such a confined space, gravity reaches extreme levels. It aligns with the principle that more mass means stronger gravity. Earth's gravitational pull keeps us grounded, with mass dictating the strength of that pull. However, when we compare Earth's gravitational force to that on the Moon, astronauts appear to weigh less. Why? The Moon's size translates to a weaker gravitational pull, making everything on its surface feel lighter in comparison to Earth, mapping the anatomy of black holes. The compressibility of black holes introduces a captivating and puzzling concept. It's astounding to consider that a star akin to our Sun can collapse, leading to the creation of a black hole occupying a volume comparable to that of a modest-sized city. The immense density resulting from this transformation poses a formidable challenge to human comprehension. For perspective, while the Sun spans roughly 1.4 million kilometers in diameter, a small city typically covers only about 10 kilometers. This significant reduction in volume highlights the extraordinary change from an entire star to a black hole. This emphasizes that while we colloquially refer to them as holes due to their gravitational impact, it doesn't fully encapsulate their true nature. So, if black holes aren't just empty spaces, what exactly are they? From a technical perspective, black holes can be defined as spherical entities characterized by two primary components: the singularity at their core and the theoretical boundary called the event horizon. The singularity represents a point of virtually infinite density without any volume, exerting an overwhelmingly strong gravitational force that defines black holes and shapes their unique features. This singularity, nestled at the center of a black hole, showcases an exceptional degree of smallness and density. To visualize, imagine standing at the North Pole of our planet. The stronger gravity in the northern hemisphere compared to the southern hemisphere illustrates the inverse relationship between gravity and distance. This dynamic interaction with Earth's gravitational pull reveals that we don't experience a uniform force at all points. Areas closer to us exert a more potent gravitational pull, while those farther away have a weaker effect. However, compressing Earth's entire mass into a smaller volume would intensify this gravitational force. Crucially, the total mass remains constant. What changes is the density. Higher density means a more concentrated mass and subsequently a stronger gravitational pull. Understanding this interplay between black holes and gravity reveals their enthralling nature, challenging our grasp of space, time, and the governing principles of the physical universe. Black holes persist as captivating subjects, fueling extensive exploration and research in this intriguing field. The esteemed theoretical physicist Michio Kaku has dedicated decades to pursuing a comprehensive theory known as the theory of everything. Among the many ideas in this domain, one shows significant promise: superstring theory. This theory seeks to unify gravity and radiation by proposing that subatomic particles are incredibly small, vibrating strings. It imagines the universe as a symphony of these strings, akin to distinct musical notes corresponding to different vibrations of a violin string. Likewise, various particles in nature align with specific vibrations of a superstring. What sets superstring theory apart is its ability to distort spacetime, giving rise to phenomena like black holes, wormholes, and other intriguing solutions stemming from Einstein's equations as these strings move through time. This theoretical framework not only reconciles Einstein's gravitational theory with quantum theory, but also sheds light on numerous mysterious natural events. However, a puzzling aspect of this theory lies in its requirement for 10 dimensions within spacetime. This stark contrast to our everyday perception of 3 spatial dimensions and 1 temporal dimension seems confounding. To comprehend these extra dimensions, consider a 2-dimensional pond inhabited by fish that only perceive length and width. In their reality, height is unimaginable. But when raindrops disturb the pond's surface, the fish notice ripples, indirectly acknowledging a 3rd dimension. Similarly, physicists propose that we cannot directly perceive these additional dimensions of space-time. Instead, we can detect their influence on our familiar world. Specifically, the vibrations of strings within superstring theory generate energy waves traversing these hidden dimensions. These waves manifest as particles with distinct properties like mass and charge. This offers the potential for superstring theory to explain all observed particles and forces, including the mysterious realm of gravity. However, a significant challenge stems from the incredibly tiny scale of these extra dimensions required by superstring theory. Unfortunately, direct exploration remains elusive as our laboratories can only precisely measure the 4 dimensions we commonly encounter: length, width, depth, and time. The intrigue and influence of black holes' event horizon. In cinematic depictions and visual presentations, the event horizon often takes the form of a shadowy circular boundary in space, encapsulating our typical understanding of a black hole. This boundary signifies a crucial threshold, often termed the point of no return, encircling the central core. Anything that crosses this boundary faces an immediate and unstoppable gravitational pull towards the core, without any conceivable means of escape. Despite its appearance as a tangible perimeter, it's crucial to understand that the event horizon lacks physical substance and holds no contents within. It's essential to recognize that black holes don't adhere to traditional object characteristics, primarily consisting of vast emptiness. The singularity at the core contains all the accumulated matter, while the surrounding space remains mostly void, creating an illusion of profound darkness. Any material or energy entering the black hole swiftly moves towards the central singularity, merging with it almost instantaneously. The gravitational force exerted by black holes is extraordinarily powerful. Its strength is so immense that even light cannot evade it, making black holes impervious to direct observation. Therefore, instead of conventional telescopic tools, scientists must rely on large-scale radio telescopes and gravitational wave detectors to indirectly detect and study these enigmatic cosmic occurrences. In 1915, Albert Einstein introduced a groundbreaking concept that revolutionized our understanding of how objects in motion affect the fabric of spacetime. This profound insight merged the previously separate realms of space and time. Think of it like disturbances spreading across the surface of a serene pond. Fast forward to 2025, a century later, a momentous breakthrough occurred at the Laser Interferometer Gravitational Wave Observatory. For the first time in history, scientists directly observed gravitational waves. This incredible achievement stemmed from the collision between 2 black holes that occurred 1.3 billion years ago. Black holes make their presence known through their significant impact on the surrounding celestial environment, particularly their ability to attract and superheat gas, dust, and stars. As these materials get pulled toward the black hole, they emit detectable radiation, appearing as thermal signatures. In April 2019, the Event Horizon Telescope, comprising 8 terrestrial radio telescopes specifically designed for capturing black hole imagery, achieved a historic milestone. They successfully imaged a black hole and its surrounding shadow for the first time. The focal point of this groundbreaking image was the black hole within the Messier 87 galaxy, a significant component of the Virgo galaxy cluster. The captured image depicts a luminous ring encircling the black hole, situated approximately 55 million light-years away from Earth, boasting a mass 6.5 billion times greater than that of our Sun. This glowing ring, referred to as the halo, represents the intense thermal emissions generated by the swirling hot gas close to the event horizon, the outermost edge of the black hole, before succumbing to its irresistible gravitational pull. Theoretical scenarios of black hole travel. When contemplating the potential ramifications of a person being engulfed by a black hole, it becomes apparent that such an event would carry profoundly adverse consequences. Irrespective of the specific classification of black holes encountered, the prognosis remains overwhelmingly dire. To hypothesize a scenario where an individual impulsively ventures into a stellar mass black hole without any intervention, the resultant physical transformation would involve a distressing process known as spaghettification. Despite the seemingly whimsical name, the reality of this phenomenon is far from amusing. The immense gravitational pull of a black hole would compress the individual from head to toe while simultaneously stretching their body, leading to a configuration reminiscent of stretched spaghetti. Considering the potential scenarios, opting for entry into a supermassive black hole does present a relatively less catastrophic outcome. Let us contemplate whether for the pursuit of scientific inquiry or as a monumental leap for humanity, the case of an individual choosing to descend into Sagittarius A, a supermassive black hole positioned at the core of the Milky Way. This celestial entity, initially observed by astronomers Bruce Balick and Robert L. Brown in 1974, and later officially named in 1982, boasts an estimated diameter of roughly 44 million kilometers and a mass equivalent to 4.31 million times that of our Sun. The expedition into Sagittarius A star begins once an individual crosses the event horizon, a definitive boundary signaling the irreversible point of no return. Inside this boundary, the surroundings are perceptible to the traveler, but observers outside are unable to glean any information. Light emitted from within is trapped and redirected inward, rendering the individual invisible to external observers. Encouragingly, despite the intense gravitational force within such vast black holes, the tidal stretching effect is comparatively milder, reducing the likelihood of being stretched into spaghetti-like strands. It's crucial to emphasize that these scenarios exist purely as theoretical constructs, owing to the extreme nature of black holes, making direct observation and exploration unfeasible. Nonetheless, the study of black holes continues to captivate scientists, deepening our understanding of the intricate mechanisms governing the universe. Escaping from a black hole presents an immensely challenging task, if not outright implausible. However, a glimmer of hope emerges through the concept of white holes. While black holes draw matter inward, white holes expel it, although their precise nature remains enigmatic. Thankfully, there are conduits called wormholes that theoretically connect black holes and white holes. These wormholes propose the potential for traversing from a black hole to a white hole, albeit over billions of years. It's crucial to acknowledge that this concept remains in the realm of theoretical exploration and refinement. As per Kaku, it's prudent to temper expectations and avoid reckless endeavors solely based on this theory. While the ideas of white holes and wormholes hold immense fascination and promise for interstellar travel, they are speculative and require extensive scientific inquiry and development. Resisting the gravitational depth. Within the enigmatic confines of a black hole lies a fascinating realm ripe for exploration, despite the gravitational entrapment it imposes. This environment offers a unique opportunity to expand human understanding through experimental endeavors. These endeavors might potentially challenge the traditional notion that matters inexorably collapse into a singular point within a black hole. Instead, an intriguing alternative surfaces: the concept of a Planck star, a theoretical proposition stemming from loop quantum gravity. It's crucial to recognize that loop quantum gravity itself resides within the domain of speculative scientific theories. Its primary aim is to construct a quantum framework that elucidates the fundamental force of gravity. Within this framework, spacetime is conceptualized as being quantized, composed of discrete and finite units or chunks. These units operate at an extremely minute scale, giving the appearance of continuous movement on a macroscopic level. The concept of spacetime granularity offers two crucial advantages in our understanding of the cosmos. Firstly, it furnishes a coherent explanation for integrating gravity within the framework of quantum mechanics. Secondly, it acts as a barrier preventing the formation of gravitational singularities at the heart of black holes. As matter succumbs to the unyielding gravitational pull and collapses within a dying star, it encounters resistance owing to the discrete nature of spacetime. This resistance imposes a limit on matter's compression, preventing it from shrinking beyond the Planck length, approximately 1.68 times 10 to the power of -35 meters. Consequently, everything that plunges into a black hole is compacted into a dense entity, but not reduced to infinitesimal proportions. This resistance halts further compression, leading to a cessation or reversal of the collapse, a process that might be described more aptly as a cessation rather than an explosion. This phenomenon implies that black holes exist as transient entities with a finite lifespan. However, owing to the extreme time dilation effects near black holes, their demise unfolds over an immensely protracted period, spanning billions or even trillions of years when viewed from the external universe's perspective. This temporal dilation presents an intriguing facet of black holes' existence, offering a glimpse into the immense timescales and cosmic dynamics within these enigmatic cosmic entities. The concept of a Gravastar emerges as a proactive approach aimed at tackling the perplexing issue of singularities, steering away from reliance on unverified quantum gravity theories. Despite its seemingly ad hoc nomenclature, astronomy occasionally adopts such naming conventions. However, it's crucial to discern a fundamental distinction between a black hole and a Gravastar. The latter is characterized by the presence of dark energy rather than a singularity. Dark energy, a pervasive cosmic entity extending through both space and time, instigates an expansive force pushing outward. Though it might appear akin to science fiction, dark energy's existence is an established reality. Currently, dark energy actively fuels the accelerated expansion of our universe on a cosmic scale. In the case of Gravastars, as matter cascades into them, it encounters a formidable barrier in the form of dense interior dark energy, impeding penetration beyond the surface. This contrasts sharply with black holes, which possess an event horizon, an essential boundary from which nothing, not even light, can escape. Recent observations conducted by gravitational wave detectors like LIGO and Virgo during black hole mergers have cast uncertainty on the existence of Gravastars. This uncertainty stems from the distinct signals emitted during the merging of Gravastars, diverging from those produced by merging black holes. These detectors continue to amass new data, intensifying doubts about the plausibility of Gravastars. It's pivotal to clarify that Gravastars aren't explicitly prohibited within the framework of our universe. However, their theoretical foundation remains precarious, subject to ongoing scrutiny and assessment. The ongoing evolution of scientific understanding and the acquisition of new observational data remain pivotal in discerning the potential validity of these theoretical constructs within our cosmic reality. Now, it's time for today's subscriber pick. Theoretical physicist Michio Kaku has explored various hypotheses, including the concept of black holes as gateways to other universes or containing a singularity. But direct observation or conclusive evidence of their interiors remained elusive. In a momentous revelation that has left the scientific community gasping for breath, Kaku unveils the unthinkable. We finally found what's inside a black hole. You see, recently there's been an exciting development. A brand new black hole was spotted as it tore apart and swallowed a star that got too close. This happened in a small galaxy a million light-years away, during what's called a tidal disruption event. The TDE became visible when it released a strong burst of energy, shining brighter than any other stars in that galaxy, giving scientists a chance to learn more about how galaxies and black holes are connected. This finding also introduces a new intermediate black hole for study, helping us understand more about their sizes. It's a big deal in the cosmic world, sparking a lot of interest and promising to push our knowledge further. What do you make of this? Ring singularities and wormholes. The landscape of singularities doesn't solely revolve around Planck stars and Gravastars. Researchers have introduced an alternative perspective rooted in a deeper understanding of black holes, diverging from the concept of a single point of infinite density. This alternative perspective arises from our comprehension of non-rotating, uncharged black holes, admittedly less captivating in their attributes. However, genuine black holes, especially those endowed with angular momentum, exhibit captivating behaviors. The rotation of a spinning black hole, as predicted by Einstein's general theory of relativity, distorts the singularity into a ring-like structure. Transitioning through this ring singularity opens the possibility of encountering a wormhole, potentially leading to emergence through a white hole, unveiling an entirely new and exhilarating cosmic domain. Yet, challenges arise within the interiors of rotating black holes due to their inherent instability, a consequence of their rapid rotation. This instability engenders significant centrifugal forces akin to anti-gravity, which exert a pushing effect rather than a pulling force. Consequently, an inner horizon emerges within the black hole's confines. Within this region, external radiation is compelled by intense gravitational forces to move inward toward the singularity. Paradoxically, the radiation experiences anti-gravity effects near the ring singularity, induced by the centrifugal forces at play. The inner horizon assumes pivotal significance as a boundary. Any interaction with it would expose an individual to an intense burst of radiation brimming with infinite energy, encapsulating the entire history of the universe in a fleeting instant. This paradoxical interplay between gravity, radiation, and the ring singularity within rotating black holes presents a captivating avenue for exploring the profound mysteries of our cosmos. Refining models through black hole collisions. The emergence of an inner horizon marks the initial stage in the formation of black holes, yet the existence of rotating black holes poses a significant challenge to the precision of our mathematical frameworks, suggesting the presence of unique and uncharted phenomena. Thankfully, the advent of a groundbreaking concept, gravitational waves, has granted us a pioneering glimpse into the enigmatic interiors of these cosmic giants. This recent scientific endeavor promises to profoundly enhance our comprehension of the cataclysmic events that transpire when these cosmic entities collide, a spectacle of unparalleled rarity and cosmic significance. In 2015, a monumental achievement was realized as scientists detected gravitational waves for the first time. This feat was accomplished through the utilization of intricate and monumental instruments designed to monitor disturbances in the fabric of space-time, originating from the collisions of black holes. The repercussions of such collisions reverberate throughout the cosmos, akin to the waves generated when agitating a sealed container, offering insights into its contents by analyzing resulting sounds. In the realm of gravitational waves, these perturbations arise from the intricate dance of two colliding black holes, providing invaluable information for scientific scrutiny. As a result, scientists have utilized these measurements to refine their models of celestial events, enabling a deeper dive into the internal dynamics governing these cosmic phenomena. Moreover, this data allows for a meticulous examination of the validity of Einstein's theory of general relativity in extreme cosmic environments. Until recently, the foundation of scientific models rested predominantly on linear interactions, providing a basis for their predictive abilities. While effective, these models inherently carry limitations, failing to encapsulate the diverse array of behaviors inherent in complex systems. However, an ongoing exploration into nonlinear interactions presents a compelling opportunity to significantly enhance these models, potentially boosting their precision by up to 10%. This advancement holds immense promise, particularly in the realm of detecting colliding black holes, promising scientists greater accuracy and confidence in identifying and studying such events in the future. The progress in understanding nonlinear interactions represents a substantial leap forward in our unyielding quest to unlock the mysteries of the universe. By integrating these newfound insights into gravitational wave detection techniques, we edge closer to the next frontier of exploration. This advancement possesses the potential to enrich not only our understanding of gravity itself, but also to illuminate the awe-inspiring phenomena unfolding within the vast cosmic expanse. As our comprehension deepens, so too does our ability to unravel the intricacies of the cosmos, ushering in an era of expanded knowledge and exploration into the fundamental nature of the universe. Unveiling the tidal disruption event. The Laser Interferometer Gravitational Wave Observatory, renowned for its groundbreaking discoveries of gravitational waves, faced an operational hiatus since 2020 due to the pandemic. However, upcoming system reactivations bring hope for an enhanced capacity to detect and delve deeper into the study of black holes. A recent study conducted at the University of Michigan, spearheaded by Enrico Rinaldi, delves into the fascinating concept, proposing that black holes might possess an analogy to holograms. It's important to clarify that this analogy doesn't present black holes as fantastical projections from science fiction. Instead, it utilizes holography as a tool to explore the intricate relationship between the interior and exterior of a black hole. This research builds upon the principle of holographic duality, a concept that mathematically equates gravity and particle theories. Gravity theory operates within the realm of the third dimension, while particle theory corresponds to the second dimension. Both dimensions are integral in comprehending the intricate workings of black holes. In the year 2020, astronomers detected the tidal disruption event flare, marking the initial observation through the Young Supernova Experiment, a specialized astronomical survey designed specifically to identify transient cosmic occurrences, including supernova explosions. The prompt identification of a black hole beginning its feeding process by engulfing a nearby star served as a crucial catalyst, sparking an international collaborative effort. This joint initiative was spearheaded by scientists from the University of California, Santa Cruz, and the Niels Bohr Institute, with astronomer Charlotte Angus standing among the prominent contributors to this groundbreaking endeavor. The collective efforts of this research team led to a significant milestone: the precise determination of the black hole's mass. The precision achieved places the black hole's mass within the range of 100,000 to 1 million times the mass of our Sun. Notably, before this discovery, tidal disruption events had predominantly served as tools for estimating the masses of massive, supermassive black holes. However, this groundbreaking achievement stands as the first instance in which TDEs have effectively revealed the masses of intermediate black holes, particularly those within smaller to mid-sized proportions. The initial observation of the remarkably swift flare assumes a pivotal role as a benchmark for future measurements concerning mid-sized black hole masses. Capturing the mid-sized black hole in the process of devouring a neighboring star unveiled information that would otherwise have remained concealed. The flares emitted by these black holes provide crucial insights into the realm of intermediate black holes, which could potentially constitute the majority of black holes situated at the centers of galaxies. Scientists theorize that supermassive black holes, significantly larger than our Sun, might have formed through the amalgamation of smaller intermediate black holes. In the early universe, these intermediate black holes likely resided within smaller galaxies. As these galaxies merged or were absorbed by larger galactic entities, their black holes combined, leading to their growth. This cyclical process contributed to the formation of the colossal supermassive black holes now prevalent within most galaxies. An intriguing question in astrophysical inquiry revolves around the prevalence of intermediate black holes in all small galaxies. The challenge lies in the elusive nature of black holes, as they become observable only when actively consuming matter or disturbing stellar objects due to their light-capturing characteristics. This poses a hurdle in identifying these intermediate black holes within smaller galactic systems. The exploration of intermediate black holes represents a significant frontier in understanding the evolution and makeup of galaxies. Unraveling the mysteries surrounding these cosmic entities promises to shed light on the intricate processes that have shaped the universe's structure and dynamics over cosmic timescales. Outro. Thanks for watching, and we'll see you in the next one.